Hi everyone, I'm Isiki. Today we'll continue with the topic of boundary condition.
Hi everyone, in today's topic we are going to talk about boundary conditions. Okay, now let's talk about boundary conditions. Okay, so before that, we have learned so many equations to calculate the electric field. Okay, for example, for point charge, okay, we can apply these equations, okay, to calculate the electric field to the point charge. And for infinite line charge, we can use these equations. And for infinite surface charge, okay, so we are going to use these equations. And when we have volume charge distributions, okay, we can use these two equations, okay, depend on whether the R is less than A or the R is greater than A. Okay, so all these equations, if you observe it, you will find that it is dependent on the epsilon naught. Okay, so by default, okay, we always use the epsilon naught. Okay, so this epsilon naught represent that, okay, this electric field is in the free space. Okay, free space. Okay, so when there is a change of the property of the material that the electric field is propagating, okay, we are going to modify, okay, these epsilon naught, okay, parameters. Okay, for example, we have found the electric field from a structures that is equals to, for example, 2x, okay, plus 3y, plus 4z. Okay, for example, this is the electric field that we get, and we know that this electric field is propagating in a free space. Now, if I'm asking you, okay, what happened to this electric field when it crossed to different material? For example, okay, initially it is in the epsilon naught, and now this electric field is going to propagate through another material, okay, another dielectric, which has different dielectric properties. So what will happen, okay, what will happen to this electric field in the new environment? Okay, if this is the only information that you have, you could calculate this electric field by using the boundary conditions. Okay, so this is where we apply these boundary conditions. That is to find the electric field that is in another regions, okay, in another mediums. So first of all, let's look at the definitions of the boundary conditions. Okay, so boundary conditions. So if an electric field exists in a region consisting of two different media, okay, so now you have two different media. So like I mentioned just now, so might be one with property epsilon 1 and the other with epsilon 2. Okay, so this electric field exists in a region that consists of two different media. Okay, so electric field coming here, might be going here. Okay, so the condition that the field must satisfy at the interface separating the media are called boundary conditions. So at this portion, there is a condition that must be satisfied by the electric field. Okay, at the boundary of two medium, we call it as a boundary conditions. Okay, so based on this boundary condition, we are going to determine the electric field in another medium given the electric field in the first medium. Okay, so these boundary conditions can happen for many interfaces. Okay, that could be separating the dielectric and dielectric, for example, like what I'm showing you here. Okay, you have dielectric 1 and dielectric 2. And it could happen between a conductor and dielectric, meaning that here you have one conductor and here you have dielectric. Okay, so there are two mediums and conductor and free space. Okay, might be this one is replaced with free space. Okay, free space. So these are the conditions that we can look at it. Okay, so and the interface between the two mediums. Okay, so to apply these boundary conditions, so first of all, we have to break our electric field into two orthogonal components. Okay, so the meaning of orthogonal is that, okay, the electric field ET and the EN, okay, they are 90 degrees. Okay, so this is the meaning of orthogonal. So this N represent the normal components, okay, the normal component, and this T represent the tangential components. Okay, so you have to break the electric field. So this is your electric field. You have to break it to normal component and also tangential components. So what's the meaning of normal component and tangential components? Imagine this blue line is the interface. It's the interface between dielectric medium 1 and dielectric medium 2. So when the electric field, okay, is having a 90 degrees angle with the interface, we call it as a normal component. Okay, on the other hand, if the electric field, okay, is having 0 degree, you see, is parallel, is 0 degree, we said that this is a tangential component. Okay, so we have to break it into tangential and normal component. Okay, let's look at the derivations of the boundary conditions. Okay, so now you look at this diagram. So you have a medium 1. So you have medium 1 and also medium 2. Okay, each of them is having different dielectric properties. And E1 represent the electric field in medium 1 and E2 represent the electric field in medium 2. Okay, so every E1 and E2 we break it into normal component and also tangential components. Okay, you can see how they are labeled. If it is E1N, means that this is the normal electric field in medium 1, and this is the tangential electric field in medium 1, and this is the tangential electric field in medium 2, and this one is for medium 2, normal components. Okay, you can see how it is labeled. Okay, so in order to define what is the conditions of the electric field at the boundary, okay, we have to apply line integrals of electric field around a closed rectangular path A, B, C, D, A. Okay, so I hope you can find this A, B, C, D, A, B, C, D, A. Okay, so it's a closed loop. Okay, so you are going to integrate this closed loop. Okay. Okay, so this is a line integral. So you see this is a line integral. Okay, so you are going to integrate it in a closed loop. So first of all, you will integrate it from A to B. Okay, A to B. Okay, and then B to C. Okay, B to C, C to D, and D to A back. Okay, and according to the conservative of electric field, if you perform the electric field in the closed loop, okay, it is equals to 0. Okay, so meaning that if this thing, you perform the line integral of electric field in the closed loop, it is always 0. Okay, so when we expand this thing, okay, let's expand it. Okay, so this one is going to take your E multiply with the length AB. Okay, so for the length AB, because this is B minus A, right, when you perform the integrations, okay, we label it as the delta L. Okay, so this delta L is coming here, okay, the length. And then for this one, B to C, I can see this. From D to C, actually, it is break into two mediums. Okay, one is in medium 2, one is in medium 1. So we break it into two parts. Okay, so this E, okay, now we are taking the E2 normal component because all the E that is in these directions, okay, in this direction is the E2N, okay, is the E2N. Oh yeah, just now is E2T, yeah, E2T, because E2T is in these directions, right? Okay, it's in these directions. Okay, so just now is E2T, so is this E2N is going to multiply the length. The length is delta H, okay, over 2. okay, as well as this one, but this one happened in the medium one, okay. And the next one, C to D, okay, from C to D, the direction is opposite with the direction from A to B, okay, so you will have a negative. Okay, so from C to D, it is in the, you are using the E1T, okay, because the E1T is in these directions, okay, you have to take the E1T, okay, E1T multiply with the length, and for the D to A, see D to A is coming in this way, okay, so this is a D to A, so it's coming in this way, okay, opposite to the directions over here. This one is going up, this one is going down. So when you are coming integrating from this point to this point, okay, you are using the E1N and in the opposite directions, okay. So here you have a E1N, opposite direction give you negative, okay, and this is the length over here, okay, the length over here is del H over 2. Okay, so when you're doing this thing, expanding all this, simplifying everything, okay, finally you will have this one. Okay, so imagine if this thing is approximate to 1, okay, this one is approximate to 1, okay, so this one will give you, wait, it's not approximate to 1, okay, this one you bring it to the right, okay, this one you bring it to the right, then you will have E2N minus E1T, okay, if you bring the E2T to the other side, you will have these equations. Okay, so this equation is telling you that the tangential components of medium 1, it must be the same as the tangential component of medium 2. Okay, so when you apply this formula, okay, you could simplify this one to this. Okay, so this is the first boundary condition that you must remember when you're, because we were going to use this thing. Okay, so next we look at the second derivations of the boundary conditions, okay, which is based on the Gauss law. Okay, so for this one, okay, we are going to consider the electric flux. So same like the electric field, you can break the electric flux, okay, into two components. One is normal component, one is tangential components. Okay, so by applying the Gauss law says that, okay, the flux coming out from the surface, okay, so this one will be the surface, okay, you draw a cylinder and this is the surface, okay, so the flux coming out from the surface will be equal to the charge enclosed by the surface. Okay, so this one is depend on the charge distribution, the rho x, on this surface. Okay, so this one is the rho x located at the surface. Okay, not this one. Okay, the rho x is located here. Okay, so the rho x is over here. Okay, so for this Q, we can get it by multiplying the rho x with the area of the surface. Okay, and for this left-hand side, the total flux coming out, we will have flux coming out from the top, okay, bottom, and also side. Okay, so usually the side, okay, it will be 0, okay, because we assume that this thing is very, very small, so the side can be ignored. Okay, right, so now we will have a top and bottom. Okay, so for the top, okay, it will be considering this one, okay, multiply with the area, okay, because this is the area, right, this is the area, so multiply with the area, so minus, because it will be opposite directions, this one will be going like this, opposite directions, okay, following the directions of this one, okay, so minus the D2, the D2N, okay, normal component with the area, so you will have this one. So this is coming from here. Okay, so we have this thing, if we simplify it, okay, so this is the second boundary conditions. Okay, second boundary condition, and you can relate with the electric field, okay, by using the formula D equals to epsilon E. Okay, and if there is no surface charge at the boundary between two interfaces, you can assume it to be 0, and you can just apply this formula. Okay, so this is a second. Okay, you can either use this one or this one, depending on the conditions. Okay, so this is the second boundary conditions. Okay, second boundary conditions. Okay, so from this boundary condition, we can actually estimate what is the angle that the electric field met with the interface and normal to the interface. Okay, so you see here, we can break the electric field into tangential and normal components. So there will be angle that the electric field E1 met with the normal components and also tangential components. Okay, you can easily find this angle by using the trigonometry. Okay, for example, you can look at this one. This is the first boundary conditions, E1t. So E1t is over here. Okay, you can find this E1t or represent this E1t by using this formula. Okay, same as for the E2t. Okay, so for the second boundary conditions, you can apply the same things. Okay, D1n, okay, D1n is here. Okay, D1n, and this is D2n, and this is D1, sorry, this is not D2n, D1n, okay, D1n. Okay, you can also apply this formula, trigonometry, and relate it with the epsilon E squared. Okay, and when you continue to simplify everything, consider everything, okay, dividing the 1 by 2, okay, you can get this. So this is the angles, okay, for of the electric field, okay, met with the interface. Okay, you can always apply this formula. Okay, so this is basic about the boundary conditions. Okay, in our coming class, okay, we will try exercise, then you will know how to apply these boundary conditions.